POVM element is just this, rho be indexed by small m over the sum of possible quantum states at the channel output, and this is the non-commutative quotient. So you can see that this POVM element is somehow proportional to the sense state rho be indexed by small m. It's linear in the argument on in the numerator. So that's a pretty good measurement. Okay, so let's see how to prove the established one-shot bond. So given a realization of the code book C, that the error probability is just by Bond's rule. It's 1 over capital M, so uniform prior probability for each message, and rho b x is the same state, and this identity minus pi dx is just the trace of the whole thing is just the error, and we sum over all possible capital N states in the code book. Then we just plug in the definition of the critical measurement by this. We just plug in this into pi, and then we obtain this. Here I intentionally write the same state in the blue color, and in the denominator of the critical measurement, I split this sum into the rho bx and the sum of all the other states x bar indexed by x bar not equal to x on purpose. Okay, then you just calculate this identity minus this guy is nothing but the numerator becomes this red dot. Okay, so if we want to upper bound this error, we just need to calculate the trace for each x. Okay, so let's do that. We need to focus on this guy. Then the point here is that if you recode the lower bound to the non-commutative minimum and fill in this rho bx as the blue part as a and operator a, and all the sum of other states as the operator b, then you just use this trace inequality. So c, this rho bx is a, and the other thing is b. Okay, and then because now those x and x bar, they are random variables, so you will take expectation over x and x bar condition on x. If they are mutually independent, so then this is just expectation over x bar. Okay, then I move this conditional expectation, the red part, inside the trace of the non-commutative minimum. And why we can do that is because the non-commutative minimum is jointly concave in the operator. So by Jensen's inequality, we take expectation inside, we are getting larger, so we are in the right direction. We just move it inside. Okay, and how to calculate this guy? Then we use the pairwise random code book because we just take expectation. So, and the expectation is just rho b we saw before. And there are how many sum in this? There are n minus 1, many those guys, so we got n minus 1 rho b. And essentially we are done. We will calculate this quantity and take expectation. And in the last step, if we use the direct sum structure, and then we can move, this guy is equivalent to the trace of the rho xb, the joint state, against the product of the marginal and the n minus 1. So we are done. That's the whole proof. Essentially, it's just a 3-line proof. So let me summarize the proof in the following diagrams. So suppose that I will send the message rho b x1 at the channel output, and the red ones are all the other alternatives, other states. Then the POVM element of the critical measurement is like this. We have seen it before. So this means that we are deciding the same state rho b x1. Then let's see the complement of it. Identity minus this pi b x1 is just this quotient. In the numerator, you can see that it is the sum of all the red part. So the key observation in this paper is the following. Using the critical measurement to distinguish multiple states at the channel output is exactly equivalent to using the critical measurement for a binary hypothesis testing between rho B x1 and all the other states, the sum of all the other states. Also, so I interpret this as a 1 versus the raised classification traces, and it's equal. They are all equalities in the deviation. So there are no bounds at this moment. Okay, so that's the whole thing. But we know that the error using critical measurement is suboptimal, so I just translate it into my favorite non-commutative minimum equation, because it's the optimal error. So here it means that we're calculating this optimal error between rho B x1 and all the rest of the states. However, oh really, 5 minutes? Okay. Okay, so, but here on the right-hand side, all the other states are actually complicated because it depends on code book, rho B x1 to the rho B xm. So the sum of it could be complicated. So we just take the conditional expectation, and then all the other states will be averaged to the same marginal state at the channel output. So we can see that why random coding is very useful in the error analysis. And then we just take the expectation for the same state and equivalent to the discrimination, binary discrimination between joint state and the product state. So we can interpret this upper bound as the minimum error of discriminating rho x b and n minus 1 rho x tensor rho b. So let's see the implication of the result. This yellow part is the established one-shot bounds. If we use the upper bound to the non-commutative minimum, like if we use the channel bound, we can get an exponential form for this error probability. Here, I don't want to write explicitly the exponent. If the channel is additive, it's IID, then we'll immediately get exponential decay. We call this a large deviation regime. If the rate is not a constant, we will get some refined version for the moderate deviation regime of state Z. And if we use some, we can also express this bound in terms of some hypothesis testing divergence, which is an SDP. So we can compute this, and this leads to the tightest one-shot channel capacity so far. If we use some second-order expansion, we can get the second-order rate in a small deviation regime. We can also get some moderate deviation regime. On the left-hand side, there are one-shot bounds, and they can lead to the improved asymptotic bounds so far on the right-hand side. So let me explain the figure in the following. So the x-axis is the transmission rate. Here is the channel capacity, and the y-axis is the error probability. If you use channel just once, then maybe the curve is maybe the best you can get. If you have the resources to use channel many times, then you can get sharper and sharper bounds. If you fix the rate here, then the result shows that we can get some exponential decay we call large deviation regime, like this. Then the rate, this curve will converge to the channel capacity at a speed of 1 over square root n. And for these two corners, we get both the conversion from rate to capacity and error to vanish. It's called a moderate deviation regime. And on the left side is we call it achievable regimes. Okay, and I don't have any time to go to the applications, but the proof applies to entanglement. We got very similar results where the theta is the entanglement. It is one-shot capacity so far. But I don't have time to go to the proof of entanglement assistance, but okay, and you also channel, broadcast channels, and multiple access channel. We have multiple access channels, and also classical data compression with quantum site information.
Sorry, I noticed that we made a mistake, so maybe you don't have to slow down. Sorry, don't have to speed up so much. Okay. Let me give you an additional 5 minutes, yeah, if you wish to say a bit more.
Okay, so okay, let's go to the conclusion.